I'm Eric Scheidley, and this is Astronomy Fundamentalized, Lecture 2, Scale. In this lecture, I'll talk about the big and small of the universe and how astronomers get their minds around those extraordinarily large numbers. I'll also pose an interesting question about the place of man in our universe. I like to pose a notion that there are really only four fundamental properties in the universe. What I mean by a fundamental property is a principle of how our universe is constructed and put together that can't be reduced to some more simple concept. These are the foundation stone ideas of our universe. And I put them here in a list: mass, time, length, and charge. It occurs to me that I could just as well say space for length. But an important point that I'm going to try and make here is that each of these things is measured by mankind, and there are units that we use for their measure. Mass is typically measured in kilograms, but there are other units that you can measure mass in: grams, slugs, grains, depending on the practical application that you're using mass for. Time also has fundamental units of seconds, but for astronomical purposes, it's not surprising that we might consider hours, or eons, or millennia. Length is typically measured in meters, and certainly meters are only useful for terrestrial applications. When I start talking about the distances between planets or stars or galaxies, then other units of measurement come into play, and they are the kilometer, the parsec, and light years. Now, electric charge is also a fundamental property of the universe, not terribly useful in astronomy, although there are some phenomena, such as the northern lights, which are explained in the context of this fundamental property. Nevertheless, for the sake of completeness, I put them on my list and say that charge is measured in coulombs. My point here is that every other concept that we develop in science in general, in this case astronomy, but in all sciences, is in some way based on a combination of these fundamental properties. As an example, let me point out velocity. You might look at my list and say, well, velocity is missing from your list of fundamental properties. Well, the reason why it's not here is because in order to calculate a velocity, I take a certain length in space and divide by the time it takes to cross that length. In that way, speed or velocity would have units of meters per second. That is, velocity is made up of the more fundamental quantities of length and time. Every other quantity that you'll encounter in your astronomy textbook, or anywhere else for that matter, is going to be some combination of mass, time, length, and charge. These are the fundamental properties of the universe. When we go about measuring these things, there's a number associated with the measurement. For example, I'm 2 meters tall. And that's a very convenient way to describe my height, because a meter happens to be roughly the same size of me, so there are only two of them in measuring my height. By the way, yes, it's true, if you work that out in your head, 2 meters is quite tall. I stand about 6'6", going on 6'7". So 2 meters is rather tall, but for the scale of a human being, a meter is a good approximation. There are things in our universe, however, that are much, much smaller and much, much larger. When we do that, our units of measure turn out to produce very, very large numbers or very small numbers indeed. Here's a very large number that you might recognize. 602 and a whole bunch of zeros is Avogadro's number, the number of items in 1 mole. Usually the items are atoms or molecules, as you may have studied in chemistry. This number is very inconvenient to write in its standard form, and so we write it in scientific notation, writing it as 6.02 times 10 to the 23rd. The important thing here is that the 10 to the 23rd gives us an idea of the bigness of the number. And we should note immediately that 10 to the 23rd is 10 times larger than a number followed by 10 to the 22nd. Now, there are all kinds of rules for calculating with scientific notation, but for our purposes, in this basic astronomy course, we're just going to want to pay a heads up to the bigness and smallness of numbers because, as we learn about astronomy, we will encounter very large numbers indeed. Here I have a table that contains the listing of the SI prefixes for numbers written in scientific notation. The prefixes are familiar from about 10 to the 6th to 10 to the minus 6th because you recognize micro, milli, centi, deci, deca, hecto, kilo, mega. These are familiar numbers because they're the numbers of the everyday scale of life on Earth. Numbers like giga, which is 10 to the 9th, have only become familiar recently as our hard drives get large enough to contain a sufficient number of bytes that it becomes convenient to write them in the 10 to the 9th format. You may even heard recently about tera and petabytes in the world of computation as things really get out of control there. But as of yet, we haven't heard about exa, zeta, or yotta bytes. I'm sure sometime in the future Apple will release an iPod that has 8 yottabytes of storage capacity so that you can contain every piece of music ever written in the history of mankind. On the small end of things, beyond micro, 10 to the minus 9th, nano, pico, femto, atto, zepto, yocto. These are numbers that you don't encounter every day because of the world of the very small. But if you were a scientist who was studying molecular structure, for example, units like picometers and nanometers and even femtometers would not be surprising. These coefficients, therefore, give us an idea of the size of numbers, and I should appreciate that when I talk about microbiology and talk about nanobiology, I'm talking about a difference of 10 to the first, difference of a factor of 10. I'm sorry, I said that wrong, actually. Difference between micro and nano is 10 to the third, so it's 1,000 times difference between micro and nano. You see, it's important to make sure that you have your scientific notation clear in your head in order to describe the bigness of numbers. That is, anything that is nano is 1,000 times smaller than anything that is micro. Another word about mass, the first of my 3 really important fundamental properties. Mass is fundamental for a very important reason. It's defined only in terms of its measurement. Here I've shown a very sophisticated pan balance that's for sale, where I take a massive object and I place it on top of the tower there, and it reads off a certain number of grams. What does that actually mean? What is mass? Once I've measured the mass of an object, what have I learned about it? A middle school answer to this might be, well, you've learned the amount of stuff that's in it. It's often said that mass is a measure of the amount of stuff. Well, that's a little bit unscientific, and we immediately correct it by saying, well, maybe. What we've done is identified that mass is a measure of the amount of matter in an object. It would not surprise me at all if you could find a science textbook that would say that mass is a measure of the amount of matter. This definition of mass is completely inadequate, and I'll explain why. If I have an object that has a certain mass, you would say it's a measure of the amount of matter. But I know that the object is composed of atoms. And you say, well, that's not a problem. Atoms are matter. Every atom has a mass because atoms make up matter. Well, atoms themselves are made up of smaller particles, protons, neutrons, and electrons. If I consider the electron has a mass. You cannot say that the mass of the electron is the amount of matter in the electron because an electron is matter. It is a fundamental constituent of matter, and so that would be defining itself. It makes no sense at all. The reality is that mass is a measure of a property of matter known as inertia. When I measure the mass of an object, I'm measuring how much inertia that it has. Inertia is an object's resistance to acceleration. Now, that's an issue of physics associated with Newton's first law. Nevertheless, I've measured a property of matter that has no deeper explanation. All I can say about the mass of objects is that I can put them on a pan balance and faithfully determine a number by sliding some sliders back and forth or by some electronic thing that goes on. But the mass is a measure of the amount of inertia, and it has no more fundamental definition. You may have heard in recent news about the Large Hadron Collider and the search for the Higgs boson, otherwise known as the God particle. This research is significant because if the God particle is in fact discovered, it gives us a deeper insight into mass and gives us a notion that mass may not in fact be fundamental, that there might be something more simple and clever going on behind the scenes in the universe. But for the moment, mass is defined only in terms of its measurement. And in our universe, there are some things that are quite small indeed. Electrons, for example. Electrons are not the smallest particle that we know of, but their mass is 9 times 10 to the minus 31st kilograms. A very, very small mass indeed, and a good reason to use scientific notation to describe the number. Human beings, on the other hand, have a mass on average about 80 times 10 to the 0 kilograms. It looks funny that I should write the scientific notation this way, 80 times 10 to the 0, when 10 to the 0, in fact, anything raised to the 0 power is 1. What I'm saying here is that the average mass of a man is only 80 kilograms. The important point is that an electron is 10 to the minus 31st and a man is 10 to the 0. That means that a man is 10 to the 31 times more massive than an electron. The scientific notation makes it possible for me to understand the scale of numbers. The largest thing that I can think of is the entire universe itself, which is, according to modern estimates, about 10 to the 53rd kilograms. That is, 10 to the 53rd times more massive than a human being, which is an extraordinarily large mass indeed. You may wonder, how is it that they can know the mass of the universe? Well, just like this diagram here, which is a cosmological model created by astrophysicists, we have some understanding of the construction of the universe, its density and evolution, and it makes it possible for us to estimate the mass of the universe. The details of that we'll leave for a later lecture. Time has a sort of similar thing going for it that mass does. It's defined only in terms of its measurement. Stop and think for a moment. What is time? As I give this lecture, there's an instant that I would call now. And here's another instant, which is now called now, because the old now is now in the past, and the now is in the present, but only for an instant, because then it immediately becomes the past as the future becomes the present. Obviously, it's very complicated, very sophisticated, and try not to think about it too long. Because time, like mass, is defined only in terms of its measurement. There is, for the moment, no deeper answer than that. You build a clock, there are two things that occur, and your clock meters out, by the sweep of a second hand, for example, the length of the interval in time, in seconds, defined only in terms of its measurement. Here's the smallest time that I thought to come up with. It may not be the smallest, well, who knows what the smallest time is, but the amount of time it takes a photon to cross a proton is a clever enough time to be interested in. And this is 1 times 10 to the minus 43rd seconds, a spectacularly small time. The painting here, by the way, is an original painting done by Tilman Brooker, associated with one of the Nobel Prize awards. I can't remember which, but the line down the middle is associated with the Planck time. That very thin blue line it represents that very, very small interval. The curious thing about it is that in the scale of the picture, the line is nowhere near thin enough. And in fact, it would be impossible for Brooker to have painted a legitimate representation of the thin interval of time that is 10 to the minus 43rd seconds. In comparison, the human heartbeat is about 0.8 times 10 to the 0 seconds. Once again, I've used 10 to the 0, so 0.8 of a second is about the average human heartbeat. By the way, yes, that is the heart exhibit at the Franklin Institute, which those of us who live in the area of Philadelphia probably have fond childhood memories of. The human heartbeat, which is which I give as a good scale of the biology of human life on Earth, is about 10 to the 0 seconds. It turns out that the protons that make up atoms don't live forever. They in fact decay and disintegrate into smaller components. And the half-life of a proton is 1 times 10 to the 42nd. There's an astrophysicist by the name of Sir Martin Rees who came to Drexel University and gave a talk on the state of cosmology. And in that talk, he suggested that if one was to try to come up with a notion of the ultimate age of the universe, like how long the universe will exist. He suggested that a way to define that would be once all the protons that exist currently in the universe have disintegrated, and he calculated how much time that would take and determined that it was, prepare yourself for this, 10 to the 10 to the 76th seconds, which is a spectacularly long time, a number so extraordinarily large that even scientific notation becomes inadequate using 10 to the 10 to the 76th. Length is the same deal. As you listen to this lecture, I'm somewhere in the world right now. There is a distance between you and I. There is space between you and I. You are at one location in the universe, I'm at another. What does that mean? What does it mean that there are different places in the universe? It's another one of those things. If you think about it too long, you'll just go nuts trying to figure out what it means that there's space. It's another one of these things, fundamental aspects of the universe that are defined only in terms of how you measure them. We lay out some meter sticks between you and I, and now we can say that the distance is however many kilometers. Some people listening to this lecture are on the other side of the world from me now. The radius of the Earth is 6,400 kilometers, so they're 12,800 kilometers away from me, roughly. Some people might be right down the block, and I'm not aware of it. At any rate, the amount of space between us can be measured and described in terms of length. But that's as far as it goes, because space is a fundamental property of our universe. Now, protons are extraordinarily small. They're about 10 to the minus 15th meters across. But if you think about these images here are quantum mechanical descriptions of the probability density of measuring electrons, it turns out that electrons aren't little particles like billiard balls the way most of us tend to think of them. But there's a science of the very small known as quantum mechanics, in which the description of these particles, and another is quantum electrodynamics, where the description of these particles is done and the sizes can be estimated or described on average, and it's about 10 to the minus 15th meters. Human height, on the other hand, is about 1.6 times 10 to the 0 meters. I wonder if you can see the human being in this painting. This is Marcel Duchamp's nude descending a staircase. And if you look carefully, you can see the head and the shoulders and the arms and the hips and the legs of a person descending a staircase, a person in dynamic motion. Still, a person is about 1.6 times 10 to the 0 meters. As I mentioned, I'm about 2 times 10 to the 0 meters. Nevertheless, again, the human height has a scale of 10 to the 0, 10 to the 0 being 1. Now, we look out in the universe in order to find the furthest galaxies away that we can find, to give us a definition or an idea of the scale of our universe, how large the thing is in general. The current estimate is about 2 times 10 to the 26th meters, the furthest galaxies away that we've ever seen. And so indeed, the universe is quite large. Here's the interesting point of the whole discussion. You may have noticed that in terms of everything that matters, the fundamental properties of the universe, mass, time, and length, the scale of human existence is 10 to the 0. There are things in this universe that are fantastically more massive and spectacularly less massive, fantastically longer in life and spectacularly smaller in period. There are things that are amazingly far away and sizes that are smaller than our imagination. And yet, strangely enough, the scale of human existence is directly in the middle of the scale of our universe. It's a curious question for which no one has an answer. Our place in the universe is directly in the middle, and we look to the large scale and we look to the small scale as we continue to investigate and study astronomy.